Good day, good evening, good morning, everyone, everybody in the room. Thank you very much for attending today's session on OneQuantum Africa, Africa's Quantum Strides event. So today we will try to have a public aspect, professional aspect of how to engage within the quantum realm or the African quantum realm. But prior to that, so since we have, I can actually point out some of the quantum beginners in the chat. Okay, but since we already know that some of you wouldn't really know not that much about quantum, and that's why we have today our special guest, Malak Ghriani. She's a very special, very special member in Q Libya, and also OneQuantum Libya, and she will elaborate on that. Her own successful story, how she got into quantum, being only 18 years old. So without further ado, Malak, the stage is yours. Show us about who you are, what is the word quantum, and why should African cares,
Of course, yes. Hello, everybody. I'm Malak. First of all, Malik, my screen sharing does not seem to be working, and I would like to share my screen.
Okay, could you try now?
Yes. Yes, thank you.
Okay.
Hi, everybody. I'm Malak, and today I'll be talking about just what is quantum computing, how I got into quantum, and how you can get into quantum as well. It's just going to be the base information so that you can keep up with the conversations later on in this session, and I hope you will enjoy. First of all, let's talk about who am I? Why should I be telling this to you? Why would you trust me? I'm Malak Ghriani. I'm Libyan, and I first studied about quantum computing 2020 with QXQ, which was the first quantum computing course for high school students taught by MIT and Oxford professors, sponsored by IBM. So we had a year-long course where we just learned about all the basics of quantum computing, algorithms, and how they work. And as soon as I finished that course, I went around seeking for communities in Libya. And I found Quanta LY, OneQuantum, and Q Libya. And I found Malik, Abdul Malik. And right away, I wanted to try to advance my quantum information and try to connect business with quantum, try to learn more and add more to the quantum community. Now, today I wanted to talk about computers and why we're doing quantum. So, to do that, we need to go back in time and talk about computers' evolution. So, first, we started with the first generation of computers from 1830. These were large computers, like the size of a room. They had tubes, they were very expensive, slow, and used binary. And then after that, we had the second generation of computers, which used transistors. Now, these were smaller, cheaper, and faster. They also used the very first programming language, but they were still not as good as the computers we have now. Then we had the third generation, which used integrated circuits. These were way smaller, way cheaper, accessible. They used programming languages, keyboards, and monitors like the ones we have now. And as you can see in the picture, it's more like what we see now. They were just boxes instead of a room-sized computer. Then we have the fourth generation computers, where we are now, which use microprocessors and are extremely small, like a phone. This is a computer right here. They got way smaller, they're way faster, they use graphics, they have a large memory. So as you can see, we're getting smaller and stronger. So in our, I think, journey into getting smaller and stronger and faster, we are meeting a physical end. The parts of a computer are about to reach the size of mere atoms. Now, to see why that is a problem, we might need to clear up some basics. computers are made from computer chips. Chips. These chips are made from basic modules, and the modules are made from logic gates. Now, logic gates are just created by transistors. This is the basic basis of every modern computer right now. Now, you can think of a transistor. You can think of a transistor as an on and off button. You can have basically electrons going through, and it basically either has it on, electrons pass through, or off, electrons don't pass through. And that's basically it. So let's say it's off, that's a 0, it's on, that's a 1. So now we can have multiple transistors and we can have a string of zeros and 1, which will basically create everything from the Zoom call we're on to the video to the audio. It's all strings of zeros and 1s. So transistors are the very base. But the problem is that transistors, we're trying to get them smaller and smaller. Right now, I think the normal transistor is about 14 nanometers big, which is 500 times smaller than a red blood cell. That is extremely small. But we're trying to get, yet again, smaller. The problem is that once you get to the size of a few atoms big, physics no longer makes sense. You can think of a transistor like a wall or a barrier that stops electrons from passing through. But if we get only to a size of a few atoms large, barriers are no longer working. That is because of something called the quantum tunnel effect. Imagine this is the barrier and the electron is here. The electron can basically ignore the barrier and pass right through to the very end. Now, that defeats the purpose of the transistor, and we are now stuck in a problem where transistors no longer work. The bases of our computers are useless once we get into the smaller world. So now, what should we do? Should we just stop trying to advance? No, we're humans. We keep adapting. We keep moving forward. So what will we do? How about using the quantum physics that is being a problem to our own advantage? With that, we get to quantum computers. Quantum computers use the weird properties of quantum physics to compute and to basically get better and faster. Now, these three quantum properties are as follows. We have superposition. Let me just get a smaller pen. Superposition. I think I misspelled that. Yeah, it's without a T, I think. Whatever. Superposition, which states that something can be in two states at once. For example, let's say we have a box. Now, this box can have a ball inside, and someone tells you the ball is either red or blue. In our physical world, let's say the ball is red. No matter what happens, the ball will always be red. It's a red ball. That's what it is. In the quantum world, the ball is both red and blue at all times until you open the box. So if the box is closed, the ball is a mixture of red and blue. It's both those two colors. It's a gradient, I'll say. But then once you open it, it decides whether it wants to be red or blue. So for example, if we have this ball and we repeat this experiment about 100 times, you'll find that once you open the box, 50% of the time, or 50 times, it was red, other 50 times, it was blue, the same ball. That means the ball is both those colors until you look at it. Now that is superposition. It shows that it can be more than one thing at one time. Now that is a game changer because normally we use bits, which are either 1 or 0. But with quantum computing, we use qubits, which are both 1 and 0. So we have 1 and a 0 at the same time. Now, for why that would be useful is because let's say with a classical computer, we would have 2 bits, and they could either be one of these four possibilities at once, each time. With a qubit, it can be all of these four possibilities at the same time in parallel. So if we have only just 20 qubits, we can have about 20 million possibilities, 1 million possibilities in parallel at the same time. Now, that is an exponential increase in speed. That's why superposition is a very big game changer in quantum computing. The other property is entanglement. Now, entanglement states that two qubits are connected with each other. And if we change one of them, the other one is also changed, no matter the distance between them. So if we have one qubit here on Earth, another qubit on the moon, and we do something to the qubit on Earth, the one will change. So the way I like to make that more intuitive is imagine we have another box. I love my boxes. And we have a glove, a pair of gloves in this box. This is one pair of gloves. And over here we have another pair of gloves. So if I open let's say I give one box to Malik, and I have him move somewhere far away from me, just all the way to the other side of the earth if he wants to. Phones between each other. I don't know anything about him. I don't know where he's gone. But if I open my box and I see that I have the right sleeve, now I know he has the left sleeve, even if he didn't open his box. Just because I know what's in mine, I know what's in his as well. Now, I only saw this one. So that's what quantum entanglement is. Just by checking one qubit, you can know the properties of the second qubit. The third quantum property is interference. Sorry about my spelling, I'm not sure if it's wrong. Interference is, I'm sure you took that in waves. So say we have one quantum system or one qubit in this wave, and one is in like that. So if they interfere with each other, they can either cancel out or add to each other. They can either cancel out or add on to each other. Now, this is useful if we want to get rid of a specific state that we don't want or a specific value. We can have it interfere with another one where they cancel each other out. Or if we want to just read a specific number and we have it positively interfere and we have it increased. Now, these are the three main properties that we use in quantum mechanics and quantum computing. And because of these, computing is way faster and way more powerful than a normal computer. Now, that might bring on the question, will this replace everyday computers? We said that they're faster, we said that they're stronger, we said that they're better. But will they replace you watching cat videos or YouTube or gaming on your normal computer? Not on the foreseeable future. I don't think so. I think we're probably set. We're good with what we have in our normal everyday life. But they have potential in the scientific field. They have potential in the smaller things that scientists and specialized people use. For example, data. With a normal computer, when we have a database search, for example, it will have to go through each one of the components to find what you want. So let's say the worst case scenario is that we'll have to go through each one. So let's say here we have about 100 items in this database. A normal computer, worst case scenario, will have to go through each one of these 100 items to find what you want. But a quantum computer only needs square root of that time. So just 10 times going through the list. Now that is very big once we have a large number of data. For example, if let's say we had 1 million pieces, right? With a classical computer, that would take it about 1 million times to go through the list. But for a quantum computer, it's only 1,000 times. We already cut the last few zeros. That's a huge change. So that is with even larger and larger, like when we go to governments and citizens, that's going to cut the time way shorter. Another cool use I find is of simulations. Particles are very, very difficult to simulate because they don't follow our physics, right? They follow quantum physics. So for a normal computer to simulate them, it takes a lot of time and it's normally not very accurate, especially when it comes to bigger molecules. The accuracy goes down the bigger and more complex the thing we're trying to simulate is. So why not simulate quantum physics with quantum physics? By using quantum computers, we have a higher accuracy with simulating um, structures. So hypothetically, we will be able to get insight on proteins that we didn't have before that might revolutionize medicine. So with quantum computers, we'll be able to simulate much bigger, more complex structures and molecules in more detail. Now, the question is, will this be a very specialized? Blah. Question is, what is possible with this? Will we just have bigger, better AI, or maybe even teleportation? Honestly, we're not really sure. Will it just be a specialized tool for scientists to use to increase science, or will it revolutionize all of society for all humans out there, where every person can have a quantum computer in their hands? We're not really sure. The only way to know is to find out, is to learn more about quantum computing and to advance this field. And anyone can do that. You don't have to be a tech genius or a tech savvy or a mathematical genius. There are multiple ways to learn more about quantum computing. I can tell you these three ones, which I have used quite a lot. QWorld, they give you multiple courses. And workshops, they're just for free. There's IBM Quantum. They have multiple online free notebooks that are just out there. You can just look at them, you can read through them. They also have a lot of free YouTube videos just on the internet. You don't need to pay for anything other than maybe a few ads you have to bear through. Other than that, IBM Quantum and Qiskit have multiple videos online for free that you can just learn about the basics of quantum mechanics, quantum physics, and quantum computing. And it's very easy to go through. It doesn't matter, even age, doesn't matter how old you are. I'm 18. I'm learning about this. And I've been learning since I was 16. Honestly, the resources are out there and we should use them. Right? I'm very grateful that we have these things. And since we have them, we should be able to use them to our ability. Thank you very much for listening. And I hope quantum computing is a bit less complicated, a bit less, weird or intimidating as it used to be.